Hey guys, today we'll be looking at rational exponents and radicals, which is p.3. So to start, a rational exponent just means that our exponent is a rational number, which means one integer over another. Before we get to this, we just had this definition that says a to the n equals b, says that b to the 1 over n equals a. So one example is that if we want to figure out what 8 to the 1/3 is, well, we need to figure out some number that we raise to the third, or cube, and get to a. And we know that 2 cubed equals 8. So now we know that 8 to the 1/3 has to be 2. Alright, and this, for odd numbers, there's only one possible solution, so this is going to be our only one solution to 8 to the 1/3. Alright, and if we have a rational exponent, the way we're going to think about this is first we're going to do what we just did, figure out what a to the 1 over n is. We'll get an answer from that, and then we'll raise that whole thing to the m. So we'll do it step by step like this. Alright, so real quick, let's do this first example here. We're going to simplify this expression. All our rules that worked for integral exponents are also going to work for rational exponents. So here we have multiplication inside the parentheses, so we can distribute this 1/4 power into both of these. Alright, so this 1/4 power is going to go into the 16, so we'll get 16 to the 1/4 times y to the 12th to the 1/4. Alright, so just like we would have done last section, now to simplify the first thing, we need to find something that we raise to the 4th power and get out 16. Well, that's going to be 2. And then here we have y to the 12th raised to the 1/4. We know if we take one exponent and raise it to another, it's the same thing as multiplying the exponents. It's going to be times y to the 12th times 1/4. Alright, and our final answer is going to be 2y cubed. It's 12 times 1 over 4 is 3. So these work just like examples we did with integral exponents. All the rules work the same. It's just when we multiply things, we might get back to integrals or integers, and we'll get an answer like this. So the next thing, basically the same idea as rational exponents, are radicals. So you hear this middle rectangle here. We have the nth radical of a, so this is the nth root of a, equals a to the 1 over n. So these are just different notations for the same thing. But when we use this radical notation, we get these extra rules about how they should be simplified. So we have these 3 rules here. If we have an nth root, then we should have no perfect nth powers left inside the radical. So nothing that's a perfect nth root inside the radical. There should be no fractions inside the radical, and there should be no radicals in the denominator. So each of these 3 examples correlates to one of these bad things. So here we're going to have perfect nth powers. Here you can see we have a radical in the denominator, and here we have a fraction in the radicals. All 3 of these right now are bad. We don't want to leave them like that in terms of being simple. Alright, so here's a couple of techniques we can use in order to get our radical to satisfy these rules. So this first one, we don't have any fractions in the radical, and we don't have any division, so we don't have to worry about radicals in the denominator. So we just have to worry about getting all the perfect nth powers out. So I'm going to rewrite this. Alright, 24 is 4 times 6, so I'm going to rewrite it like that. X to the 8th I'm going to leave, and y to the 9th I'm going to leave. Alright. And down here we have these rules that work for radicals. Is say if we have the nth root of a times b, it's the same as the nth root of a times nth root of b. That also works for division, so radicals can split over multiplication and division. So here we're going to split this radical over all of these multiplications. So it's going to be the square root of 4 times the square root of 6 times the square root of x to the 8th times the square root of y to the 9th. So we just split that radical over every multiplication. Now we know 4, the square root of 4 is 2. This is 2 root 6. Now x to the 8th, remember the nth root of a is the same thing as a to the 1 over n, so this is the same thing as x to the 8th to the 1/2, and this is the same thing as y to the 9th to the 1/2. And just like we did here, when we have one exponent raised to another exponent, we multiply. So our final answer is going to be x to the 4th, y to the 9/2, and then 2 square root of 6. And you can rewrite one of these y's as a square root of y and get left with y to the 4th times the square root of y, but most of the cases with variables, we just want to leave it as a rational exponent rather than square roots. Alright, so that's an idea of how you can get rid of these first things. We have perfect nth powers inside the radical. This next example, we have a radical in the denominator. So to get rid of this radical, right now it's a square root. So we need to get rid of this square root of 2 in the denominator. So the way we're going to do that is multiply by the square root of 2 over the square root of 2. And remember, this is 1 because these would just cancel. It's the same thing as 1. And we multiply anything by 1, we get back to what we started with. So this thing here doesn't really change what we're working with. Alright, so now when we multiply this, the numerator, we get 4 times the square root of 2. Alright, but in the denominator, the square root of 2 times the square root of 2. Well, if we go backwards from this rule, I'll write it out. We can combine these two separate radicals into a single one. So this is square root of 4. Alright, and we know the square root of 4 is 2. So really, we can think about these square roots just canceled out. Alright, so we get 4 square root of 2 over 2. Now 4 over 2 is 2, so we get 2 square root of 2. Alright, so whenever you have a square root in the denominator, you're going to multiply by what you need to cancel it with, and you need to multiply by 1 so you don't actually change the expression at all. So we multiply by the square root of 2 that we need to, but then over, or under in this case, the square root of 2. So we're multiplying by 1 so we don't actually change anything. Right, and we get this final answer, which doesn't have any perfect square roots or perfect squares. There's no fractions in the radical, and there's no radicals in the denominator. Alright, and now the last example we're going to do, we're going to use this property down here that says radical split over division. So we're going to split this over the division. Alright, so that's the first step. So now we already did this middle step. There's no fractions in the radical anymore, but we still have radicals in the denominator, and we have some perfect third powers left. So y to the 6th, that's y squared cubed. So this is going to be y squared. Alright. In the denominator, we can split radicals over multiplication. So this is the third root of 25. And the third root of x cubed is just going to be x. Alright, so we're almost completely simplified now. The only problem is that we have this cube root of 25 left. So the way we're going to get rid of that, again, we're going to multiply by 1, so it don't actually change the expression at all. Alright, but the one we need to multiply by, here 25 is 5 squared. We need to get a 5 cubed to get the perfect cube, so we're going to multiply by the cube root of 5 over the cube root of 5. Alright, because we need 5 more, another 5 in here will make the inside of this a perfect cube, and then we can get rid of the cube root. So now I have y squared times the cube root of 5 in the numerator. In the denominator, this 5 will multiply by that 5. Alright, we'll get the cube root of 125. Alright, times x. And again, like I just said, 125 is 5 cubed, so it's going to cancel out with the cube root, and our final answer will be y squared times the cube root of 5 over 5x. Alright, so this is an example of getting rid of everything that we need to. So we got rid of the fraction to start by splitting the radical over the fraction. We got out all the perfect powers that we could, and then the final step was to get rid of the radical in the denominator by multiplying whatever we could to get this to be a perfect cube so that it would pop out of the cube root. Alright, so those are the methods to help simplify radicals. So remember, whenever you have a radical, make sure you satisfy all three of these conditions to say that it's perfectly simplified.